Thank you everyone for joining again. This is part one of the Atomic Clock series of the overall Quantum for National Security's TAC lectures this year. This is the fourth lecture that we've put on. And if my screen will advance, there we go. So we've already heard our series of lectures on Rydberg RF receivers. And we're now moving on to Dr. Stephen Jefferts, who will give us the introduction about atomic clocks. To remind everyone what the purpose of these lectures is, the Quantum for National Security TAC is a very broad organization with technical experts in quantum sensors, but also a lot of people that are approaching the quantum industry from a business perspective or from diplomatic efforts and export control. And we're trying to have these lectures as a way to give everyone a common understanding of the technologies that are being discussed so that we can all contribute to the national security conversation. So to that end, the first lecture in every one of these series is about the sensor operation and the key performance parameters given to you by what I consider to be the best individuals to make those introductions, and Steve Jefferts really fills that role for atomic clocks. So before we get started, this is a benefit that we are putting together. This is a public lecture that anyone can join, but this is being put on by the Quantum Economic Development Consortium and a subgroup within that called the Quantum for National Security Committee. QED-C was launched by the National Quantum Initiative Act back in 2018. Members across 39 countries, and we would love for your membership as well. So if you find this useful, there are some lectures that are members only, and so you would have access to those if you come join us and contribute to the national security conversation. So the link for membership is there, and we will move on. Again, this is Dr. Steve Jefferts is going. His background, he had a long career at NIST prior to joining Northrop Grumman. He led the development of the NIST F1 and F2 clock primary frequency standards, which were the primary frequency references for the United States and critical to calibrating time, the rate of international atomic time. He was also the primary scientific leader for the NASA Primary Atomic Reference Clock in Space program and designed the physics package for the Italian cryogenic primary frequency standard. Those clocks together provided the most accurate direct measurement of the black body radiation shift ever performed. And of course, he's a PhD in physics from the University of Colorado. So the point here is that Steve Jefferts is a mainstay in the quantum atomic clock community and the quantum sensor community more generally, and we are very lucky to have him talk to us today. So Steve, I'm going to let you share your screen, and I'm going to go on mute for everyone else. There will be a 10-minute, 15-minute Q&A session depending on how long Steve's talk goes. As you listen, please raise your hand or put something in the chat, and I'll do my best to call on you when the time comes. Take it away, Steve.
Thanks, Eric. The first thing I should say is there are lots of people in the community who could give this talk, certainly as well as I can. In fact, the guy you're going to see next week could certainly do it. But while he's certainly as expert at this as I am, he's much more expert in what he's going to talk to you about next week, which is what do you use these clocks for within the governmental and commercial application space. And so this is a good division of labor. I need to start a little bit. Well, there we go. Sorry. I need to start with some acknowledgments. There's a long list of people here who've contributed to my understanding of these things over the years. This is certainly not inclusive. If you're in the audience and I forgot your name, mea culpa. As I said, this is not inclusive. If it was inclusive, we'd be here for the next hour just listing names. So going on with that, what we're going to talk about is the basic physics of atomic clocks, some quantum mechanics, the statistics and metrology required to characterize them, because that is what you see when the statistics and metrology are what you see when you look at a data sheet, when you're going to buy a commercial clock, or that lets you talk to people about what your needs are in the atomic clock community so that they can try to provide a clock that meets those needs. Then we're going to talk about what I call the classical commercial atomic clocks. These are the rubidium standards and cesium standards and occasionally hydrogen clocks that you can just go out and buy, assuming you have sufficiently deep pockets. And then we'll talk a little bit about advanced commercial atomic clocks. There's a few advanced clocks on the market. There are more coming on the market all the time. Some of these are optical clocks. Some of these are laser-cooled clocks, and we'll have a quick talk about those and wrap it up. I should say this talk is in no way complete, in the sense that there's just more material than can possibly be covered in an hour. The hope here is to give you enough tools to either talk to people in the field or go do further research on your own, with a better idea of what direction you need to go looking. So with that, what is a clock? And in my view, a clock is any source of events that occur at a regular basis. That's the oscillation part of a clock. Think the pendulum on a grandfather clock swinging back and forth. That is a regular, if it's a meter long, it's about 1 second period, and away you go. You don't have a clock from such a thing until you start counting the ticks of the pendulum, if you will. And so those are the hands of the clock, the integrator of the frequency to give you time. And so you have to have both of those in order to have a clock. And really all we've done is replace the pendulum in some sense with some sort of atomic reference. And so why are we using atoms? There are a bunch of sort of postulates of quantum mechanics that say indistinguishable particles are truly indistinguishable. And among other things, that means that if you have a sample of cesium atoms and I have a sample of cesium atoms, they're identical and indistinguishable. So if you build a clock using those things and I build a clock using those things, then everything else being equal, we should get a clock that ticks at the same rate. Now, obviously, unless we do something special, the time, the absolute time those two clocks give won't be the same, because we will have started them at different times. But at least we will agree on how often they tick forward 1 second, to say. The second reason to use atoms is that they don't change with time. And that's really a more profound statement that says we believe the laws of physics are stable in time and are unchanging over the lifetime of the universe. In fact, that's a hot topic in physics, and we turn it around and use very good atomic clocks to look for changing physics with time. So far, we haven't seen it. Atoms are pretty insensitive to the environment. Mm-hmm. For example, that pendulum clock we just talked about, if you change the temperature, the length of the pendulum is going to change a little bit, i.e. if the temperature goes up by a little bit, say a degree, the length of the pendulum is likely to change by, call it a part in 10 to the fifth. So the ticking rate changes by something like that amount. And that causes a change in the rate of that clock. Atoms don't do that. Well, that's sort of not true, but a cesium atom changes by about a part in 10 to the 15 with a 1 degree change, and it's extraordinarily predictable. And so by measuring the temperature, we can actually account for this change. But even more than that, you can go find other atoms that have much smaller changes. But we've already reduced the problem by 8 orders of magnitude just by going to cesium. And then, as I say, there are better atoms. It's fun, keeps some of us mostly out of the bars at night, and that's a good thing. So the quantum mechanics that go with this have to do with with the idea of quantized states in atoms. And when you have an atom, it's only allowed to exist in well understood discrete energy levels. It's not allowed, it can be in, say, this energy level or this energy level, but it's not allowed to exist in the intervening energy state. That's just not stable, and so it will go to one of the two levels. You have to remember that energy and frequency to a physicist are indistinguishable, and I see Microsoft got me with the standard font change. That's supposed to be a new. Planck's equation for radiation says that the energy of a photon is equal to Planck's constant times the frequency of that photon, which was the new there. And because atoms are only allowed to exist in these discrete energy levels, it takes discrete amounts of energy to move the atoms from one level to the other. In particular, to move an atom from a final level, an initial level, to a final level requires a photon of this frequency that has to do with the difference between the two energies and the Planck's constant. So those rules of quantum mechanics tell us why atomic clocks are such nice timekeepers. They're going to have very high predictability for the frequency, the ticking rate of the clock. They're going to behave the same way tomorrow as they did today and as yesterday. And in an ideal world, that would be completely true, rigorously true. In fact, the atoms still have residual sensitivities to things in the environment, like the magnetic field, gravitational effects, thermal effects, as we discussed a little bit. The electronics can cause small shifts, and how well you deal with these things, either in the physics of the atom or in the electronics, basically determines the long-term, both short-term and long-term performance of the clock. And we'll get into the details starting about now. Most of the clocks I'm going to talk about come out of atoms in this first column of the periodic table. You may recall hydrogen is the simplest atom. It's got a nucleus with one electron sort of orbiting around the nucleus. The rest of the atoms in this column are similar in the sense that lithium, for example, has 3 electrons, but the first 2 are in a closed orbital, so they pair up with each other and effectively cancel out the magnetic moments associated with those 2 electrons. So there's only one unpaired electron orbiting the nucleus, and that's true for all these atoms. So all of these atoms look like hydrogen atoms, and that's important classically because those are the only atoms that physicists knew how to deal with before the advent of big computers. It just basically, the hydrogen atom you could solve analytically to some pretty high precision or fidelity, whereas the more complicated atoms out here in the middle of the periodic table were simply too complicated to get solutions for. These days, we can approach a lot of these things numerically and get better answers. But these atoms in the first column remain sort of a mainstay of atomic physics. So what we're going to talk about is turning over the spin or the magnetic moment in the electron, that last unpaired electron. And spin and magnetic moment are sort of interchangeable. Basically, if an electron has spin, it has a magnetic moment, and they all have spin. And so if it's got a magnetic moment, you can think of it as having a north pole and a south pole. The nucleus of the atom in general has a magnetic moment. Cesium, which I'll talk about a lot here today because it's one of the atoms we commonly use, has a quite large magnetic moment in the nucleus. And so under the laws of quantum mechanics, there are two ways you're allowed to assemble this last electron onto the atom. It can either go in with its north pole aligned with the north pole of the nucleus, or anti-aligned with the north pole of the nucleus. And if you've played around with magnets, you quickly realize that this anti-aligned state shown here is going to be the lower energy state. That's the way the magnets want to sit, is in this north lined up with south arrangement like this, rather than the two of them both lined up perfectly north to north. So basically, in order to go between this state and this state, I have to either absorb a photon to get from the lower state to the upper state, or emit a photon to go from the upper state to the lower state. And in cesium, the frequency of that photon is very well known, because it's the definition of the second. And in fact, it's 9,192,631,770 cycles per second, or hertz, is the definition of the frequency of that photon. And all other frequencies are measured relative to that. So the next thing to talk about is what happens when we drive the atoms from one state to the other. And let's assume that what I'm measuring on the vertical axis here is the population of atoms in the upper energy state, that spin-aligned state, where I'm starting with all the atoms in the lower state. And I'm gonna shine microwaves on them, and I'm gonna tune the frequency on the x-axis. And as I come through resonance right onto that 9 billion and change number, I'm going to see the number of atoms in the upper state increase to a maximum and this is the resonance frequency, and then it will decrease away again as I tune further to a higher frequency. And it's this feature that we use to build our atomic clock, as you'll see, I think, in the next slide, if I remember what order I did this in. So, oh, no, I have one last thing to say about that before we go there. It's the interesting thing in the atoms we're talking about here is that both this state and this state are, for our purposes, stable. Normally, when you think about excited states in an atom, you think that they will decay. But these hyperfine states tend to have lifetimes of years. So yes, they eventually decay, but not on a practical timescale from our point of view. So we drive the atoms back and forth between these two states with our radiation, and we don't drive up and have it spontaneously decay down. And that has the feature that how long we spend making the atom make the transition has a great deal to do with how well we know the frequency. And if we drive it very quickly, very hard into the other state, then in the time domain, in the frequency domain, what we have is the Fourier transform of that, and it's very broad, and we don't know the frequency required to make that transition very well. Whereas if we very gently move it between the two states, we know the frequency quite well. The problem is that these atoms are not just sitting still while we look at them. They're moving around at the speed of sound, more or less, 100 meters per second, or maybe a little bit more, depending on how heavy the atom we're talking about is. And practical, device sizes are typically centimeters or maybe meters. So we just don't have very long to look at the atoms before they've hit a wall or done something else stupid and removed themselves from our view. So we typically are forced to go faster than we would really like, which leaves us with a relatively greater frequency uncertainty and therefore a relatively greater rate uncertainty for the clock. So having said all that, I think we know how to build an atomic clock. What we're going to do is we're going to start off with a quartz crystal oscillator here, and we're going to use it as the time base for a synthesizer. And in this case, let's pretend we're going to do cesium. So we're going to make 9.2 gigahertz. And then we're going to build some sort of a system with cesium atoms in it where we can measure how many cesium atoms are in the lower state and the upper state. And we're going to take this microwave synthesizer and we're going to sweep it back and forth in frequency like this as we sweep its center frequency. So we'll start down here and we're modulating back and forth, and we sweep to the right. And finally, as we get on resonance, you can see that on the left and the right, I measure the same relative signal amplitude or population change. When I see the same on the left and the right, that tells me I'm on the right frequency in my synchronous demodulator. So that goes into a loop filter, which controls the frequency of that original crystal oscillator. That crystal oscillator frequency is now locked on average to the center frequency of this resonance. So in the long term, the frequency of the crystal oscillator is referenced to the atoms, not to the size of the quartz, the chunk of quartz that makes the oscillator. We're moving it with this electrical tuning port. Having done that, we now have an atomic clock. The output of that clock, whether it be at 5 or 10 or 100 megahertz, is fundamentally being referenced to this 9.2 gigahertz hyperfine transition in cesium, or 6.8 if we happen to be using rubidium. Having said that, we now have a clock, and we have to talk about the quality of clocks. And there are two issues with an atomic clock. One of them is accuracy, and one of them is stability. And they're related, but not at all the same thing. The upper blue trace here is an example of a highly unstable and quite inaccurate clock. And the unstable business is the fact that every time I measure the frequency, this is my measurement time along here, every time I make a measurement, I get a different number, and it's hopping around and doing all sorts of bad things over time. The inaccuracy is the fact that it should be the true frequency for that atom is down here, and it's way up here and moving around all over the place. So the offset is the inaccuracy, and the fact that you don't even get the same answer every time you look is the instability. This clock, by contrast, is very stable. You see, I get almost the same answer every time I measure it, and I get, on average, the same measurement over time. But it has a frequency offset from truth, which, while stable, leaves it ticking at the wrong rate. So maybe this clock would gain, a nanosecond in a month or something of the sort, depending on the scale we applied here. This last clock, by contrast, is really quite accurate. It's not as stable as this, but boy, it's a lot better than this guy up here. So it's pretty stable, and it's quite accurate on the average. So the terms accuracy and stability mean very particular things in the atomic clock community, and it's important to have the distinction well understood. Now, the instability of the clock is given by something called the Allen deviation or the Allen variance, and we'll go back to this repeatedly. But the quick way to think about it is that it's the fractional frequency uncertainty. And the nice thing about having it being a fractional frequency is that now we can compare different clocks directly. If we have a clock whose center frequency is 9 gigahertz, and another clock whose center frequency is 7 gigahertz, we can compare them directly, because what we're talking about is the fractional frequency, which is another way of saying how much the clock's measurement of 1 second is off with respect to the truth, perhaps, is one way to think about it. And it's given more or less by the Q of that resonance, and I'll go back and redefine that because I didn't, I think, the first time, and the signal to noise of the clock. Now, the Q of the resonance, remember that resonance, looks like this. The Q, if you recall, is the center frequency divided by the width. So the higher, Q stands for quality factor, and the higher the Q, the better, because it says it's narrower and narrower. And the signal to noise is in these atomic clocks is generally given by the number of atoms if everything else is being done quite well. Now, here comes the problem. I can't change the center frequency once I've chosen the atom I'm using. I basically, that's the whole point is that I can't select a bunch of higher frequency cesium atoms. They're all the same frequency. So that one I'm given by the physics of the atom, and the width I'm given by basically how long I can measure on that atom in a single measurement. That's this business of how the fact that they're moving around. And then there are limits to how many atoms I can measure at the same time in a practical sense. So in order to make this number smaller, which is what we want to do, we want to decrease delta omega, and we'd like to make the signal to noise bigger for a given atom. Or, as you will see towards the end of the clock, we simply go get a different atom with a higher frequency. When you're shown a plot of the Allen variance or Allen deviation, which is more likely because it's the square root of the variance, you'll typically, for atomic clocks, see this bathtub-shaped curve. And it starts out with what's known as white frequency noise, and that averages down like the square root of the measurement time. And that makes perfectly good sense if you think back to normal statistics, right? If you measure a voltage with a voltmeter, one time you get a number, and if you measure it 10 times, you get to do statistics on that number, and the width of the distribution decreases like the square root of the number of measurements. That's that same square root of the number of measurements that I'm seeing here, which is the measurement duration. But finally, along comes probably the environment and messes up your clock a little bit. It's not quite perfectly stable. And so it turns out in the flicker regime here, you can keep measuring, but your knowledge of the frequency of the clock, the ticking rate of the clock, isn't getting any better. And eventually, if you're unlucky or the clock is of a particular variety, you will start to see it do random walk away. There are many more noise types than these three. These are the ones that typically apply to atomic clocks. If you want an in-depth review, go look at Enrico Rubiola's charts. They can be found here, and they're really a great resource for going between phase noise and Allen deviation and all of the variants of the Allen deviation, which I'm not talking about here today. So with that sort of physics introduction, I think we should blast forward into commercial atomic clocks as quickly as we can. They come, as I said before, in three basic varieties: cesium, rubidium, and hydrogen. It's not that you couldn't build atomic clocks from the other, certainly first column elements. It's that there are practical reasons for not doing it in almost all the cases. That either the frequencies are too low to be particularly useful, or in the case of francium, it's radioactive, and that's got its own set of problems. So cesium and rubidium are both the kinds of that we'll talk about, are both the kinds of clocks we just talked about. Hydrogen masers are fundamentally a little bit different. They're actually active oscillators. You can think of them as being lasers that actually laze at the microwave frequency. That's, for all the younger members of the audience who understand lasers, that's completely an accurate description, but it's historically backwards. The maser came before the laser by a few years. But more or less a cesium beam clock that you might go out and buy looks like this. This is an old picture out of Scientific American, if I recall correctly, way back in the day. But basically it works like this. We start with something down here, which is a source of cesium atoms. And cesium's interesting. It's a metal which is solid at room temperature, but just barely. It melts at about body temperature. And so it has a pretty high vapor pressure. So the way I think about this is a tea kettle that's got cesium atoms in it. and you heat up the cesium atoms and you get a plume of cesium steam, if you will, coming out of the oven. It runs into this thing called the A magnet, and we'll discuss that in a minute, but that basically separates out the upper and lower hyperfine states of the atoms, because what comes out of the source is pretty much equal amounts of both. Then maybe what I do is I take the upper state and I send them through a microwave cavity and drive them to the lower state, once again separating upper and lower state atoms with the B magnet, and I send the atoms that made the transition up to a detector. If we go into a little more detail, here's my oven. Out come the atoms. You can see the dark black ones versus the open circles are meant to represent the two different varieties of atoms. Type 1 is anti-aligned and type 2 is aligned. They get deflected opposite directions by this magnetic field gradient. That makes sense if you think about it. When the magnetic moments are aligned, the whole atom has a much bigger magnetic moment than if they're anti-aligned, because they more or less cancel. So we take, in this case, we take the aligned kind, the upper state kind, and we'll use those in the next slide. And so those come along and they go into a microwave cavity here. And if I don't have any signal, no microwaves going into the cavity, well, they come out in the same state they went in, and they get bent by the B magnet now. And since they get bent down, they never hit the detector. On the other hand, when I put some microwaves in here, I can change some of the dark atoms into light atoms here. They then get bent the opposite direction in the B magnet here, and they hit the detector. And here we go again. We've just built an atomic clock. We're going to modulate this microwave signal frequency back and forth by, a few hundred hertz, and synchronously detect how many atoms are hitting the detector and lock the microwave's frequency to the center of what maximizes what's hitting the detector, and away we go. We've got a clock. Now, this is a very good cesium standard, and this is the Allen deviation. And the first thing you're going to say is that doesn't look anything like, this. And you're right, it doesn't. And the reasons are interesting, and so we'll quickly go through those. This long period here, this long red line, is the tau to the -1/2, that white frequency noise we talked about. That's what you want an atomic clock to look like. That's just beautiful. This business back here that's happening up until a few seconds, this is the quartz oscillator all by itself before it gets locked onto the cesium atoms, which tells you, just by looking at this, what the loop attack time for that frequency lock loop that's steering the quartz onto the atoms is. It's apparently a few seconds in this clock. And then it averages down, and now this is the scary thing about log plots. We're starting up here with a fractional frequency uncertainty in the parts in 10 to the 12 at about 1 second here. And we average down, and here we are at 1,000 seconds, so 20 minutes-ish. And now here we are out here at about a day. A day is 86,000 seconds, so 10 to the 5th is about a day. That's about 10 days. That's about 3 months, and this is approaching a year, if not exactly a year, all the way out here. So you can see this clock just integrates down, and then it's apparently beginning to flatten out here. And maybe it's kicking up. This is a little hard to tell. One thing you notice is that the error bars on the measurement are growing, and that's not surprising. This is probably a several-year data set. But if you think about it, I only have the ability to compare this year to next year to the previous year for a few points, whereas I have a whole lot of, I can compare the average for this 10 seconds to the previous 10 seconds points here. So the error bars here get to be much, much smaller than the error bars out here. So this might be flat, it might be kicking up, it's hard to say, but this is what a very good cesium standard that you go out and buy will look like in the frequency domain. And to put it in terms of size, weight, and power, it's a 3U 75-pound 75-watt kind of device. They can be a little smaller, a little lighter, a little heavier, but that's the, you know, the right order of magnitude. Now, to get onto rubidium clocks, I see we're running a little late already, so I'm going to have to really kick this into gear. They work a little bit differently. We start out with rubidium atoms in a quartz discharge lamp. We pick only one isotope of rubidium. This is the one with the 7 gigahertz, 6.8 gigahertz hyperfine splitting. And then the light from this guy goes through what's called a filter cell that has the other isotope of rubidium in it. And we'll see why in a minute. It's then incident on yet a third cell that's filled with rubidium atoms plus buffer gas. And the buffer gas basically helps slow down the rubidium atoms so we can look at them for longer. And then we measure how much light is getting through the cell on a photocell. The reason this is all kind of interesting is back here in the discharge lamp, we have the two levels A and B. These are the two hyperfine levels, the spin-aligned and anti-aligned levels. And the discharge forces the atoms to go up to this excited energy level here, which is about 780 nanometers in wavelength above. That's the near infrared. And so both atoms in both states go up and then re-emit. And so you've got lots of light coming out of that discharge cell at 780 nanometers that contains both the frequency for this transition from the B state and for the A state. You then shine that light through the filter cell, which just by luck happens to have an absorption line lined up with the B state. So what happens then after the filter cell, we only have light that will couple the A state up to this upper energy level, and the light from the B state has been essentially removed. So before we put any light on here, all the atoms are basically equally distributed between the A and the B state. We put the light on, and all of the atoms get optically pumped into the B state. And the reason for that is that, remember, we have light that will connect this level to here, but no light that will connect this level to here over in the measurement cell. So atoms get excited, and once they get here, they can decay either to here or to here. If they happen to decay to B, they're stuck. There's no light left to get them to go back up to the other level. If, on the other hand, they get excited, they decay back down to A, they just get, they just get excited back up to the excited level, where once again, they can either go to A or B, and pretty quickly they all end up in the B state. And so when that happens, the light basically all gets through the cell because all of the atoms are in the non-absorbing state. They're not interacting with the light. But if I were to put some microwaves in there to change all those B atoms into A atoms, then the amount of light getting through the cell would drop, and I'd see a drop on this photodetector back here. And so here we go again. We've just built another atomic clock. We're going to take the microwaves and modulate them back and forth in frequency across the resonance. We're going to see the light in the photodiode dip and then come back in response. We're going to lock that dip to the microwave signal, and the microwaves are now fundamentally locked to the atoms in the cell. Rubidium clocks typically, this is a quite good rubidium clock. You can see it's in the mid 10 to the minus 13s at a second. And it comes out here for a few hundred seconds, maybe 1,000 seconds. It's looking more or less as if it's coming down like tau to the minus 1/2. And now it's starting to flatten out. And that's pretty typical of atomic systems contained in buffer gases and cells. They have a limited time before the environment starts causing the atomic environment to shift just enough that you mess around with the atomic physics of the clock. But having said that, that's still a pretty good clock. I mean, part 10 to the 14 means of order 100 nanoseconds in a year or something of the sort, 300 nanoseconds maybe. So, it's not so terrible. And these things can be much smaller and much simpler and much cheaper than the cesium clock we talked about previously. So these are ubiquitous and quite useful frequency standards. The hydrogen maser, I'm going to have to just pretty much skip by, other than to say this is pretty much the Cadillac of the classical atomic clocks that are available. You can see this is data from NIST, from Tom Parker some years back. You can see it's in the low 10 to the minus 13s at 1 second. And out here at a day, it's well below 10 to the minus 15. Out here at the 1 year level, it might still be below 10 to the minus 15 for a particularly good maser. It might be approaching 10 to the minus 14 for a less good maser, but still these are spectacularly good clocks. On the other hand, they're the size of a refrigerator and require extreme environmental control in order to achieve these sorts of performances. And now this is sort of an oddball, because it's a mix of a classical atomic clock and a new advanced atomic clock, but it's very definitely aimed at a very particular market niche, which is the CSACs. These are little tiny atomic clocks. They're sort of typically 100 milliwatts, 35 grams, 16 cc's, and they run over an incredible temperature range. Having said that, you see that at 1 second, they're mid 10 to the minus 10s, and maybe they integrate down for 1,000 seconds or so. And then they're not even specified. This data is taken from data sheets that are available online. The point is that if I compare that to a sort of a generic rubidium, as we were just talking about, instead of 100 milliwatts, we're talking 50 watts. Instead of 16 grams, we're talking 4,000 grams. Instead of 16 cc's, we're talking 8,000 cc's, etc. And yeah, okay, this clock is 20, 30 times better, but it's way bigger, heavier, power hungry, etc. So these CSAC clocks are awesome, awesomely good for how small they are, but they are not going to provide you with nanoseconds time uncertainty at days and years of integration time, typically. So, oh, and I just thought this is always an interesting graph. This is a couple-year period during which we measured a maser and a cesium clock at NIST against the primary standards. And you can see that the maser is extraordinarily quiet and reasonably predictable, but it's got a drift to it. And then every once in a while, it does these funny things of having steps that we never did understand. The cesium is relatively noisy by comparison, but it's much more predictable over the long term than the hydrogen maser was. Thankfully, these slides will be online, so you can go get a look at them. This is a sort of a relative performance for a bunch of these different clocks based on Allen deviation, along with a table that compares them for these classical commercial clocks. I'm going to run out of time if I go through it, so I'm not going to, and I'm going to talk a little bit about these advanced clocks. I'm going to give a very brief overview of laser cooling and a few words about optical clocks, and then we'll talk about commercial realizations and laboratory realizations. So remember we said that what we wanted to do was make the observation time long in order to make the Allen deviation small. The problem is, how do you do that? And in the old days, you built a really long atomic clock. And I have to say, Mike Garvey here is one of the grand old men in the atomic clock community. And this is Mike looking particularly groovy about 1972. And so I always show this picture when I think there's a chance he will be in the audience, because it's fun to tease him. But in any case, this was an interesting clock. You can see it's just amazingly long. And the tea kettle of cesium is down there, and the atoms come flying through here, and then they get detected in the detector down here. And you say, wow, that's going to be awesome, because I'm going to make the time incredibly long. And it doesn't work very well, it turns out, for two reasons. The first one is you kind of forgot about gravity, and the atoms fall out of the bottom of the beam, and they don't make it through the apertures on the far end of the clock so well. But the other thing is that the beam is expanding. It's sort of defocusing. So it starts out quite tight, but there's some thermal velocity in the radial direction. And so the beam gets bigger and it doesn't make it through the aperture. So it turns out that the number of atoms is dropping at just about the right rate to cancel the advantage you got here. So it doesn't work so well. So how else do we do this? And the answer is about the mid-70s, Daymelt and Wineland and Charlie Towns and somebody else, Ashkin maybe, proposed laser cooling. And the idea with laser cooling atoms is pretty simple. If I think about an atom with a laser pointed from both the left and the right here, and let's think the atom is moving left to right. If I've tuned the laser a little bit below the correct frequency for the atom to make a transition, then what happens is if he's moving towards this laser, he sees the laser on the right frequency shifted into resonance, and the one on the left frequency shifted out of resonance. So he absorbs a photon that's exactly in the direction opposite to which he's traveling. So he gets a little momentum kick slowing him down. And if he then re-emits that photon in a random direction, he's gotten a directed momentum kick to slow down and a random momentum kick in some other direction, so that in general, he's cooling off, he's slowing down like the square root of the number of photons he absorbs. And the point is that with lifetimes of tens of nanoseconds, you can scatter a whole lot of photons in a second. This works incredibly well for cooling off atoms. You can get atoms down to temperatures of millikelvin with this technique, and with variations on this technique, you can get down to nanokelvin. The temperature is important because the temperature and the velocity are fundamentally related by the half kT is half mv squared, more or less. It's three halves kT, but so that I can now slow my atoms down to centimeters a second, and I can look at them for a much longer time rather than this hundreds of meters per second. So for these commercial advanced clocks, there are sort of 4 of them that I know about on the market at the moment. 2 of them are laser-cooled microwave clocks. Now they're rubidium, I think one's cesium and one's rubidium laser-cooled. And then there are 2 optical clocks, and we'll talk a little bit about optical clocks in a minute, but think that you've replaced the microwave synthesizer with an optical synthesizer, and that will do. You can see for these 4 clocks, they actually behave quite differently. The microwave clocks start out at a relatively high frequency uncertainty and integrate down quite well over, this is one day, over days and up to tens of days, and that's as far as the data on the data sheets go. Whereas these optical clocks start off amazingly stable and just unbelievably stable at short times, integrate down out to about 1,000 seconds or so, and then turn around. This 1,000 seconds is not the optical clock per se. It is the fact that these are thermal vapor cell atomic clocks, and it's the same sort of physics problems that you saw in the classical rubidium clock, causing the frequency instability to start showing up at these times. But still, the point is that for times out to 10,000 or more seconds, these are quite great clocks, and they're incredibly robust to their environment compared to these microwave clocks. These guys need quiet, well-controlled environments, and these vapor optical clocks are, throw them in an airplane and fly them around if you want to, although they're not small. I'm about out of time, so we're going to wrap this up. Laboratory devices using optical clocks and laser cooling are ubiquitous. There's lots of them out there. I expect, will show up as commercial devices within the next few years. I think you'll be able to expect short-term AVARs on the 10 to the minus 14 averaging down as the square root of tau or better level, and long-term AVARs certainly less than 10 to the minus 16. People have demonstrated 10 to the minus 19, 10 to the minus 20. They're not likely to be cheap, but they're showing up, and they're going to get cheaper the longer people build them and as people find simpler ways of building them. What we didn't cover here is a whole bunch of things. We didn't talk much about optical cooling, past Doppler cooling. We didn't talk about systematic frequency shifts and how you get rid of them. We didn't talk about CSEC clocks, and we didn't talk about optical clocks and optical combs other than to say they exist. That's certainly a topic for another hour. And that if there's interest, you should find someone to give that talk. And with that, I'll take questions.
Right. Well, thank you very much, Steve. And we do have some questions in the chat. For anyone who would like to ask a question, that's the place to ask it, or raise your hand and I'll call on you here. I'm just going to go in order with what I received, Steve. So
Okay.
Rima asked a question here that said, this was at the very beginning of your talk, and she said, does this mean the Moscow and Boulder clocks are in sync? I don't remember exactly what this refers to.
I do. So actually, the answer is that no, the Boulder and optical clocks. Okay, so the first thing I'm going to say is I'm going to ignore gravity and general relativity for a moment, because it turns out those gravity causes a frequency shift in the clock that goes back to, well, look, we all learned it in Star Trek, right? When you go to the event horizon of a black hole, your clock stops. Well, that's real physics, and the clock in Moscow is going to tick slower than the clock in Boulder, because Boulder is further from the center of the Earth and the gravitational field is a little bit smaller. That's very measurable and predictable. So let's pretend we can correct for that, which we can. So we'll take that out of the picture. But the point is, they would not be synchronized unless we actively figure out a method to synchronize them. What they would be is syntonized, which is the word we use in this community when they are ticking at the same frequency, but that they're noon, if you will. The time on the hands of the clock is different.
Okay. No. That was a great answer, Steve. Sorry, it was me having Zoom issues in the background, finding the mute button. Okay, so we have another question here. Again, just going in order. What are the most common noises that appear at high frequencies in the Allen deviation?
Okay, so at high frequencies, let's go way back here. There we go. Sorry. So high frequencies is very short times. So you're talking about things way over here on the left of the of this Allen deviation plot. And so the first thing I would say is that at very short times, we don't use the Allen deviation. We typically talk about phase. We move into from the time domain into the frequency domain and talk about phase noise or frequency noise or things like that. And the reason for that is pretty simple. We're typically trying to lock up our active oscillator, our quartz oscillator, or our optical frequency comb to the atoms at longer times, and then keep it locked up at longer times. And so before the lock happens, which would be to the left of about this point in this Allen deviation, what you're looking at is the noise in the quartz. There's no atoms involved out in this region or even further to the left. And the Allen deviation is perhaps not the best way to talk about it. At that point, you're talking about typically electronics noise and noise in the resonator itself, if that helps.
So just before I get to the next question, A sign of a good talk, Steve. There are lots of questions. Recognize people may have to drop off, but Steve and I will stick around and get through these questions at least a little bit over time if necessary. So the next one here, Steve, is do you believe that the microwave clock will be completely replaced with optical clocks in the near future?
No, no. Optical clocks are certainly going to replace microwave clocks at the high end first, because so this is the problem. You have to build some sort of an optical frequency synthesizer. We typically call that an optical frequency comb, in order to build the same kind of atomic clock that we've been talking about, only in the optical domain. That's not a simple thing to do today. People are doing incredible research working at making that smaller and cheaper and more robust. And in the long term, I believe, yes, you're going to just all these microwave clocks will be historical artifacts. Having said that, it's been 75 years now, more than 75 years, that microwave clocks have been investigated, improved, etc. And the electronics have gotten so good and so simple for these clocks that I don't see them going away in the next few years. 20 years from now, yeah, maybe. But in the next 5 years, not a chance.
Okay. So then I have a question of, when people discuss disciplining, how is this typically done for an atomic clock?
Okay. So we can almost stay on this graph for a moment. What we're doing on this clock is, here on the left, we're disciplining the quartz onto the atoms at this point, right? We call it locking, but it's disciplining. What we do with a rubidium clock, typically, because it's typically not done with a cesium standard, but it could be, is now we say, okay, we've got this rubidium clock and it's averaging down nicely, but it's starting to drift. Do I have some way to correct for this drift? And so, for example, if I were to measure the ticking rate of this clock relative to GPS, at some point out here, GPS becomes more stable than GPS as received at my GPS receiver becomes more stable than my rubidium standard. And so I start to steer the rubidium standard to the GPS signal, which is disciplining. And there are multiple ways to do that. The simplest conceptually to me is that I simply take the rubidium standard, and within the rubidium standard is, let us say, this 10 megahertz output. And if I were to take that 10 megahertz output and reference another synthesizer that I could steer to it, I could steer the output of that synthesizer to keep it always on the frequency that I wanted it to be, as defined by GPS. And the time constant for that is likely to be hours to days, depending on the quality of both the GPS receiver and the clock you're trying to discipline.
All right. And Justin Brown asked, what are some example physical processes that lead to flicker and random walk limitations in a clock?
Oh boy. So lots of things that look like flicker in atomic clocks are the result of the environment leaking in environmental effects leaking into the physics. We used to see on some of the clocks at NIST, for example, you could watch the magnetic field in the clock change by a little tiny bit on a daily basis. And part of that is the sun coming up and moving the magnetic flux lines of the Earth around from the solar wind. And part of it is all those iron cars parking in the parking lot every morning and then all leaving every evening, because it turns out the effect is bigger Monday through Friday than it is on the weekend. And because it's quasi-random and not very big, it tends to flatten out the frequency rather than just giving you a nice, well-defined diurnal frequency fluctuation. That's an example. Temperature does the same kind of a thing because you never get the temperature really stable and it drifts, and that causes frequency drifts. I think for true flicker, as opposed to something that's flicker-like, there are all sorts of hand-waving explanations and no really good physics. And for random walk, it's almost always things in the clock aging, meaning if you put alkali metals like the rubidium or cesium inside a glass cell, eventually chemistry between the rubidium atoms and the glass cell walls can happen, and the number of rubidium atoms slowly goes down, and the background gas constituents slowly change, and that causes a ongoing frequency change in the clock. So that's the sort of thing that causes random walk. But there's no definitive list for either one of those two things.
So we've got 3 to go, and you've maintained a pretty good audience even after the hour is up. So you must be doing a good job. So Mary asked a question that's a question of how we can move from the laboratory to the submarine. What, in your estimation, is the process and speed of miniaturizing and hardening atomic clocks for use on a Virginia-class submarine? That's probably a detailed answer, but take a stab at it.
If you asked me to do that tomorrow, I would go get a fibered frequency comb. I would build a small ion trap system with the appropriate ion in it, and I would use the trapped ion as the frequency discriminator, the equivalent of the cesium or rubidium we've been talking about. I think you could quite reasonably package such a thing up in a 3U package for 100 watts kind of number, and you know, tens of kilograms, no more than that. But it would be expensive to build the first one, and it'd probably take a couple years to get it right. But I think that's a reasonable answer, and that would give you very long-term stability. I mean, it should be below 10 to the minus 16 if you choose the atom or ion correctly. If you don't need anything past 1,000 seconds, I think I would go buy one of these optical advanced clocks that are on the market now. If you want it smaller than 3U rack size, then the cost and complexity will go up significantly. On the other hand, a submarine is not a small thing, so I think 3U might just be acceptable.
So before I get to the next one here, if Vincent Bell is listening, can you respond to my comment in the chat? I'm not sure I fully understood your question. So we have a question that says, could 2 clocks be synchronized using quantum entanglement?
In the simple answer is probably not. And then the more complicated answer is probably yes, but. And I think the how to say this? The devil's in the details on this one. I think there are perhaps schemes that would be robust and allow it to work. I don't think anybody has really demonstrated such a system today.
Okay. And then can any of these clocks, I think Remo was asking about you mentioned several clocks over the course of your talk. Can any of them be networked together? And when do you think optical clocks could be networked?
Oh, all of these clocks can be and have been and are networked, including optical clocks. There's an optical clock network in Boulder, Colorado. There's a quite extensive, geographically extensive one in Europe that uses both optical clocks and laser-cooled frequency standards. That's true in Boulder as well. So yes, we can network these clocks. The quality of the networking is interesting. The highest quality networking happens with dedicated optical fibers, meaning the only thing going through that fiber is timing signals or timing signals plus carefully selected other signals, not just telecom stuff. People do manage to do various levels of synchronization using just pure telecom systems that are pretty good. And you can also synchronize using GNSS signals and dedicated microwave signals as well. That's how international time is coordinated, is using all of those techniques.
Right. So this one's going to be the last for today.
Okay.
Vincent, I didn't get a response from you, so if you still have your question, email me afterwards and I'll get it to Steve. But the last question I have on the list here is again from Justin. He says, there's a lot of attention being put on quantum enhanced measurements, like entanglement and squeezing. Do you see this being a big opportunity to improve atomic clocks? Why or why not?
Theoretically, there's no question. You can, I mean, you remember that 1 over square root of n in the Allen deviation. You can, in theory, turn that square root of n into n. And, you know, if you're talking about 100 million atoms, that's a pretty big enhancement. The flip side to that is that all the schemes I'm aware of are non-trivial, meaning they're complicated, they're typically fragile. And so while I believe we will figure out ways to do that with ever more fidelity and ever more robustness, I don't think you're going to see them incorporated on the prototypical Virginia-class submarine we were just talking about anytime soon. But the one thing I will say is this field has moved incredibly quickly for the last 30 years. I mean, it was sort of a backwater for a long time. And starting in the early 1990s, it had up until now and continuing, it has just grown exponentially in both the quality of the clocks, the size of them, meaning they've gotten both much larger and much smaller. Just the whole range of performances has accelerated tremendously, and that doesn't seem to be letting up at the moment. And so probably things are going to happen faster than I think they're going to happen, is I guess what I'm trying to say.
So Steve, I know I promised that was the last one, but I have a follow-up of my own that I
Right.
think will be a good preview of the next talk by James Camparo. You said things took off starting around the 1990s. Can you give an idea of to what happened in the 1990s that caused the takeoff?
So I would argue a fair number of things happened in the 1990s, but undoubtedly the most important from the point of view of advanced atomic clocks are the twin combination of laser cooling, because laser cooling in all its varieties allowed just a renaissance in atomic physics and the ability to measure things, which is basically, at the end of the day, really what an atomic clock is, an atomic physics experiment. That coupled with then by the mid 1990s, or even the early 1990s, the ongoing development of ways to do optical frequency metrology and very quiet lasers, meaning frequency combs, and there was an earlier technique that is still used in various places of phase locking various lasers together. That between those three things and now very quiet lasers, you can go buy a commercial laser with, you know, hertz kinds of line widths. Those three things are what drove the optical clocks in particular, but also the microwave clocks into the 10 to the minus 15, 10 to the minus 16, and now down to 10 to the minus 20 kinds of accuracy levels that are just, you know, when you start talking about frequency accuracy of 10 to the minus 18, you are no longer talking about a clock the way we all think about clocks, right? We all think about a clock as it's just something that sits in the corner and goes tick, 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 tick. But at 10 to the minus 18, if that clock is sitting a centimeter higher above the Earth's core or center, then if one of them is sitting a centimeter higher than the other, you can see it. And so these are no longer clocks the way we think about them. They're really more like space-time meters. And so a whole lot of things become possible when you have that level of stability and accuracy that just aren't possible from, you know, building gravimeters and things like that are fundamentally atomic clocks now being used for different things. So yeah, I think that's what happened in the 90s.
So I made a mistake here. Kirk McGregor has his hand raised. So that will be the last one, I
Fair enough.
promise.
Oh, that's good.
Kirk, are you able to come off mute and ask your question? If you're trying to, I don't hear you. Okay. So to the QED-C admin on the line, is Kirk forced into being mute? Is he allowed to come off?
Hey, sorry. 1 second. I'm trying to get him. There he is.
Okay.
Go ahead.
So
You should be able to talk now.
Oh yeah, thanks. Thanks for the presentation. I think you answered 1 1/3 of my questions already from answering these other questions. I guess maybe just to ask a really short one on, you know, if disciplining from quartz piezoelectric oscillations have like a few issues, are there some better physical piezoelectric oscillator candidates, or should we just switch to frequency combs if you really need to deal with something this distinctive?
Boy, that's an interesting question. Certainly the record, the highest stability oscillators out there are generated out of optical frequency combs coupled with a, you know, quiet laser. Having said that, that's a pretty complicated, expensive, possibly power hungry gadget if you're just, you know, trying to make 100 megahertz. And so I think, you know, as always, you got to decide, if you need 10 to the minus 14 at a second, yeah, that's probably your best choice today. There have been spectacularly good quartz resonators built that will do high 10 to the minus 14s. You can go out and buy one at a second. There are cryogenic oscillators that will do in the 15s at a second, but you know, you get to deal with dilution refrigerators and things like that. I would say if your business is trying to lock onto GPS signals, you don't need a high zoot oscillator like that, because the noise that you're trying to lock onto is sufficiently large. And so it's usually that trade-off that leads you to decide which local oscillator you're going to use, is what the noise in the physical system you're trying to measure is, or trying to lock onto. And if it's extraordinarily low, then yeah, you don't want to mess up its noise with your relatively noisy local oscillator. But if on the other hand, it's noisier than your local oscillator, then you're good to go.
Okay.
I'm not sure I answered the question, but it's a really complicated question. Let me try one more time. The way we usually crudely make that decision is quartz doesn't tend to average down. If I had a quartz oscillator, or most mechanical oscillators, they're just flicker from a second or maybe 10 milliseconds. There'll be a flat flicker line, and I would choose my locking point by saying, okay, here's my quartz oscillator, and it intersects my atoms at about 20 seconds. Well, that's where I'm going to lock, because at earlier times I'm doing better by not making the quartz noisy like the atoms, but at longer times, because the atoms keep getting quieter the longer I measure, I'm managing to discipline or lock the quartz and lower its noise.
Okay. I guess off of this noise rift, so even looking at Enrico's chart, do you think that noise dithering is possible, or even like possibly cancellative in a specific application?
I'm not completely sure what you're asking. There are systems where you can find noise of one type that's correlated with noise of another type. And so then you measure one and cancel the other.
Oh, I meant like dithering or canceling out, or somehow factoring out, let's say, some of this pink flicker noise with something that was blue.
Oh, whitening in that sense. Got
Yeah.
it. Yes, it works in specific cases, and it's done in some specific cases. I'm trying to think if I can come up with off the top of my head a good example, and I'm sorry, I'm blanking. But no, yes, it's a legitimate question, and there are places where it works very well. And I'm just blanking it, giving you a good example.
That's fine. I just needed to know it exists somewhere so I can look it up at some point.
Okay.
And I guess like a really third short question, if I still have time. So when you're talking about like these random walks, and these are like traditional stochastic random walks, has anyone ever really tried to look to see whether or not any of these random walks could be modulated with or redescribed as a quantum walk instead of something very stochastic? It had some other type of quantum mechanical property that could be identified?
Not to the best of my knowledge off the top of my head. And it's because, unfortunately, typically when you get to random walk, the physics is, it's, how to say this, it's all sorts of really dirty effects happening.
Yeah.
And just even sorting out which is which can be really tough, because it's aging in the cell constituents, and it is very hard to characterize that. And there's chemistry going on, and maybe the electronics is aging as well, and there's all this going on simultaneously. And I don't know that anybody has ever spent a tremendous amount of time trying to boil it down into it's this piece of quantum mechanics, because it's such a complicated system.
Sure. Yeah, no, I was just sort of poking around to see if there was potential for a good quantum algorithm to like deal with it. But okay, thanks for the questions. I really appreciate going over time.
Thanks.
Right. Well, we really have blown our schedule out of the water. So
Sorry about
thank you
that.
no, that was me. Thank you for staying. And thank everyone. You know, we still have 22 people on the line. So thank you everyone for being a part of this. And reminder that we have James Comparo next week to complete our atomic clock series. He'll be talking applications, and we look forward to having you back then. Thank you again, Steve. Thank you everyone
Thank you.
for joining.
See you next week.